This box, there's some electrical components. And if I take these electrical components in the box and I hook it up to a multimeter, I see 1.66. And that's 1.66 kiloohms. So whatever is inside this box has a resistance of 1.66 kiloohms. But it's not a single resistor. If we open up the box, it's not one resistor with a resistance of 1.66 kiloohms. It's 4 1 kiloohm resistors. And there's 2 here connected in series that are in parallel with another one, and the whole thing is in series with one here. But the entire resistance of these 4 1 kiloohm resistors is 1.66 kiloohms. So we could take these, snip them out, and put in a single resistor of 1.66 kiloohms, and electrically it would look identical. There's no way to tell once the box is closed that what's inside is not a single resistor, but 4. That's how we get at this idea that you can take a circuit and you can reduce combinations of series and parallel resistors to smaller combinations of resistors and use that to solve circuit problems. That is exactly the kind of problem we're going to look at right now. All right, so here's our problem. What is the voltage across and the current through each element of this circuit? Now let's just take a look at it. We've got certain elements of the circuit that are in series. For instance, any current that goes through this resistor is also going to go through this resistor. So these two are clearly in series. So those two can be reduced to a single resistor. Once we've got those two resistors reduced to a single one, it'll be in parallel with this resistor. Once we reduce that combination to a single resistor, this combination right here, that combination will be in series with this resistor. And so we can do a successive series of reductions of this circuit by series and parallel combinations and end up with a very simple circuit that we can solve for the current, and then we've got to put the circuit back together to figure out the current through and the voltage across each element in the circuit. Let's get started. Here's our circuit, a hand-drawn version of it. Now, here's what we're going to do. We're going to take this circuit and reduce it. So this 12 ohm resistor has a current through it. Any current that goes through that one goes through the next 12 ohm resistor in line. So these two resistors are in series. So we can reduce those two combinations of resistors by doing a series combination. And remember, the resistance, the effective resistance of two resistors connected in series is just equal to the resistance of resistor 1 plus the resistance of resistor 2. So the effective resistance of those two resistors connected in series is just 12 ohms plus 12 ohms, 24 ohms. What that means practically is this. We can take those two 12 ohm resistors and get rid of them. It's as if they don't exist. We can replace them by a single resistor, which has a resistance of 24 ohms. So our new circuit looks like this. Okay, now we can say the following. These two resistors right here are in parallel. So I've got a 24 ohm resistor in parallel with another 24 ohm resistor. And so I can reduce those two. The parallel combination reduces to a single resistance. And we know that a parallel combination looks like this. The effective resistance of the pair is equal to 1 over the resistance of R1 plus 1 over the resistance of R2. If we take those two resistors, plug in their values into this relationship, we get a total resistance, an effective resistance of the combination of 12 ohms. So what that means is we can treat these two 24 ohm resistors as if they're not there. They go away and they're replaced by a single 12 ohm resistor, which is electrically equivalent. Now we've got a circuit where I have two 12 ohm resistors. Any current through the first one also goes to the second one. They are clearly in series with each other. So, series combination, we go back to our series relationship. Series combination of the two resistors, effective resistance, R1 plus R2, 12 ohms plus 12 ohms, total resistance, 24 ohms. So we can take those two resistors and replace them with a single 24 ohm resistor. That complicated circuit that we started out with reduces to something that's very simple. It's electrically equivalent to what we've drawn right here. A single resistor of 24 ohms connected to a 12 volt power supply. Well, if I've got a 12 volt power supply, putting a current through a 24 ohm resistor, we can calculate what the current is. The current is just equal to delta V divided by R, 12 volts divided by 24 ohms, 0.5 amps, half an amp through this circuit. But the question didn't ask us what was the current in the circuit. The question asked us to find what was the current through and the voltage across each element in the circuit. To get at that, we're going to have to rebuild the circuit. So we'll take the circuit, and remember, we had a single 24 ohm resistor, but that's not how the circuit started. It started, the previous step of the calculation, with two resistors of 12 ohms that were in series with each other. And so it looked like this. I had a 12 ohm resistor here and a 12 ohm resistor there. Now that we've redone the circuit this way, we have a question for you. What is the current through this resistor, the first 12 ohm resistor, and then what is the voltage at this point in the circuit? We'll give you some choices. We know that there's half an amp coming out of the power supply. So what that tells us is this. It tells us that the current that comes out of the power supply, and that's equal to the current that goes through the 12 ohm resistor, is 0.5 amps. Now let's look at the voltage drop across that 12 ohm resistor. The voltage drop across that 12 ohm resistor, we use our different version of Ohm's law, is just this. Delta V is equal to the current times the resistance. Half an amp times 12 ohms, the difference in potential, 6 volts. So let's look at our voltage at different places in the circuit. At this point in the circuit, at the positive terminal of the 12 volt power supply, the voltage is 12 volts. But then there's a voltage drop of 6 volts across that first 12 ohm resistor. Net result, at this point in the circuit, the voltage is 6 volts. And now we're ready to proceed to the next step of the calculation. Now remember, that 12 ohm resistor in the circuit wasn't originally a 12 ohm resistor. We had originally written it as two 24 ohm resistors in parallel. Let's rewrite it that way. Now, the 6 volts stays, because that is the voltage at that point in the circuit. But I've got two 24 ohm resistors, like so, that are in parallel. And here's our next question for you. What is the current through each of the 24 ohm resistors? We'll give you some choices. The current through each of those 24 ohm resistors we can calculate this way. Look at the voltage across the 24 ohm resistors. They're in parallel, so the voltage across them is the same. At the top end of the resistors, it's 6 volts. At the bottom end, 0 volts. So the voltage across each one of the resistors is 6 volts. The current, just delta V divided by R, is therefore 0.25 amps. That's the current in each one of the resistors. Now we're going to do a quick assessment here. We said that there was half an amp that comes out of the power supply. So through the first 12 ohm resistor, there's 0.25 amps through each of these 24 ohm resistors. Look at the junction in the circuit where the current splits. Half an amp coming into this junction of the circuit, and it splits. Half of it goes this way, half of it goes this way, and the 0.25 amps in each of those branches of the circuit, when I sum those currents, I get 0.5 amps, which is the amount of current that came into that junction. So Kirchhoff's current law is validated. It works. And that gives us confidence in our result. We broke the circuit down, we're building it back up. And that intermediate step, I did a calculation to show that the 0.25 amps is consistent with what we calculated previously. We calculated it one way, and then we showed it's consistent by doing a calculation a different way. And that's assessing as we go, which is how you want to solve problems of this sort. But remember, that final 24 ohm resistor in the line was not originally a 24 ohm resistor. It was two 12 ohm resistors. So we're going to get rid of it and replace it with what it originally looked like. But everything else in the circuit that we've calculated, everything else in the circuit stays with us. So now we have two 12 ohm resistors. Now remember, we said there was a quarter of an amp that went through this branch of the circuit. We know the current that's going into this branch of the circuit. So half an amp goes to the first 12 ohm resistor, half an amp goes to the second 12 ohm resistor. And so we can calculate the voltage across each one of those 12 ohm resistors. And the difference in voltage, delta V, is equal to I times R. For each one of them, the current, 0.25 amps, times the resistance, 12 ohms, the voltage is 3 volts. So that tells us that this first 12 ohm resistor has a 3 volt drop across it. And so the voltage at this point in the circuit is going to be 3 volts. Now here's another check on our results. If the voltage at this point in the circuit right here is 3 volts, the voltage at this point in the circuit is 0 volts. It's connected by a wire to the negative terminal of the power supply. And so the voltage drop across this final resistor in line, this one right here, the voltage drop is 3 volts. But that's exactly what we calculated using Kirchhoff's law. And so that's another great check on our result. So we've taken the circuit, broke it down to calculate the current in the circuit, and then we rebuilt it. And as we rebuilt it, we calculated the voltage across and the current through each one of the elements in the circuit, checking our work as we went. The first resistor, the first 12 ohm resistor in the circuit, has 6 volts across it, half an amp through it. This resistor, which remember was a 24 ohm resistor, this 24 ohm resistor has a quarter of an amp through it, 0.25 amps, and the voltage across it, 6 volts. These two 12 ohm resistors each have a quarter of an amp through them and a voltage of 3 volts across them. That's a little bit messy, so let's redraw the circuit and put our results here. The first 12 ohm resistor, 0.5 amps which goes through it, and that gives us a voltage drop across the resistor of 6 volts. So the voltage drops from 12 volts at the top terminal of the power supply to 6 volts at this junction. Then the current splits. Half the current goes through the 24 ohm resistor, so 0.25 amps goes through the 24 ohm resistor, and the other half goes to the other branch of the circuit. 0.25 amps goes through the two 12 ohm resistors connected in series. 0.25 amps through a 12 ohm resistor gives a voltage drop of 3 volts, which gives us 3 volts at this point in the circuit. 0.25 amps through a 12 ohm resistor gives us a 3 volt drop, which gives us 0 volts at this juncture in the circuit. So we've satisfied Kirchhoff's voltage law at several points in the circuit, and we know the voltage across and the current through each element in the circuit. So we broke the circuit down, we built it back up. As we built it back up, we checked our work as we went, and we were confident with our results. The 12 ohm resistor right here, half an amp through it, 6 volts across it. The 24 ohm resistor right here, quarter of an amp through it, 6 volts across it. The 12 ohm resistor here and the 12 ohm resistor here each have a quarter of an amp through them and 3 volts across them. Our calculation squares perfectly when we're done. With this problem, the assessment was something we did as we went. We took the circuit and we reduced it to a simple circuit, calculated the voltage, calculated the current, and then we built it back up again. And each time as we went, we made assessments to check our work as we went. The net result is, when we were done, we're pretty confident that we've proceeded correctly. If we'd made a mistake, it would have come out in our work as we went. Now, another way you could assess it is to build the actual circuit, measure voltages, measure currents, and if you did that, you'd find exactly the same things as we measured, which isn't a surprise. Physics is about the world around us.